So to see how we can cast tau equal to I times alpha into a form that allows tau and alpha to be in different directions, let us go back to the definition of the angular momentum and write the velocity as the cross product of the angular velocity and the distance. So that's then what we get for the angular momentum. This expression here, m multiplying r squared omega minus r dot omega times r. If we break this into the components, this is what we get. And now let's distribute this coordinate in here, multiplying by what is inside of the parentheses. So we can write them in this form. Now we have something that multiplies omega x, omega y, and omega z in all of the three expressions. You have here omega x, omega y, and omega z. In the Ly component, you also have omega x in here, omega y in here, omega z, and the same thing for the z direction. So we can write this on a matrix form. We can write this as the angular momentum is equal to something, a matrix I, that is multiplying omega, which is a column vector. So I must be given by this expression. You multiply this by the column vector omega, and then you get to the angular momentum. So this matrix above is another example of a tensor. This is the inertia tensor. Then the relationship between torque and angular acceleration in matrix form is given by this equation, which broken in components gives you this. So as you see, a torque in x, depending on the value of the inertia tensor in the off diagonal terms, can give you angular accelerations in the other directions.